Hello, I am James Smalley, representing the jute fiber extraction team, Team Gecko, in the presentation of the jute decorticator. For some context about the problem, our machine is designed to decorticate jute, a cash crop bast fiber plant that is grown in Bangladesh and has two main sellable byproducts. The fibers themselves are the primary product and are used in making burlap, hessian, or gunny cloth. The stem is also valuable as it can be used in medium density fiberboards, and Bangladesh farmers also like to use it for fencing and supporting growing plants. This creates the goal of making an automated decorticator that can extract fibers and keep stems intact. Moving on, we address the current solutions. Current existing and marketed products are decorticators that mulch the stem and output just the fibers from the jute. These current methods have high throughputs but also large labor requirements, as you can see in the video. Moving on, I want to address our jute analog. Due to jute being grown in Bangladesh and surrounding areas, and it being out of season during the time of the capstone design course, the team needed to make an alternative to test the machine. Shown is a table evaluation matrix of a variety of bonding agents to bond jute fibers to a dowel rod, and based on the performance, a mousse-based jute analog is the best substitute the team could manage to develop for the semester. Shown is the final design for the jute decorticator. On the left is a full-scale CAD model, and on the right is the developed prototype. Moving into the CAD design, we have one main assembly and four important sub-assemblies. The first of these is the adjustment assembly that has mounted flange bearings that will hold the rollers and allow for vertical adjustment of the rollers. Next, we have the two types of rollers. The roller on the left is the gripping roller that grips jute being fed in and conveys it through the system. The next roller is the fraying roller that is used to remove the fibers from the stem. And lastly, we have the loading tray for preparing a load of jute sticks and then inserting them into the machine. Shown here is a diagram of the general machine process. Jute is fed in on the left side of the machine. The jute is then gripped by the gripping rollers and conveyed forward. The jute then comes in contact with the fraying rollers, which remove the fibers that will then fall to the floor. Another gripping roller then grabs the jute stem and ejects it from the machine. Shown are some of the key design features. The first feature is the high gripping rollers that are used to conform to varying diameter jute pieces. The second feature is the adjustable chain tensioners, allowing for system modification. Third, we have a single chain system that only needs one double-stranded sprocket to attach a power source to. Fourth is the adjustable roller heights that allow for testing of different setups. Fifth, the design has a mounting feet that allow for attachment to existing self-propelled bases. Sixth, the use of a loading tray helps make operating the machine less cumbersome. And finally, seventh, adjustable length for the machine allows for better rotation of the rollers by moving the rollers off the face of the bearings. Shown is the final prototype developed. The main notes for this are the three main assemblies developed: the flange bearing assembly, the fraying roller assembly, and the gripping roller assembly. It should also be noted that we expect for the full-scale machine to use a 15 horsepower motor. However, for testing, we use a 1.5 horsepower drill. Shown is the first assembly, the adjustment flange bearing assembly. This is made out of 090 low-carbon steel sheet metal and has slots cut into it that allow for adjustable locations of the rollers so that we can adjust the amount of grip on the piece of jute. Next, we have the roller assemblies. The first of these is the fraying roller, made from 3.5-inch carbon steel tubing with welded end caps that have bearing shafts welded onto the end. This tube features a circular pattern of sheet metal fins that have been welded on with sheets of nitrile rubber bolted on that have been serrated to offer better conforming performance. The next item we have is the gripping roller, manufactured in a similar method to the fraying roller. However, this roller instead does not have the fins and is wrapped in closed-cell polyurethane that conforms to the jute analog, providing grip against the pilling motion. Now we have the main demonstration. This is done with multiple dowel rods of varying diameters, similar to jute, and with some of them coated in the jute analog. From this testing, we see that the machine is capable of spinning up to the speed that is capable of decorticating the jute analog and depositing the fibers underneath the machine while ejecting the stems out the end. A similar test was done with a single jute analog, and the same results can be seen. Moving on, this is a demonstration of the chain system used. 6 sprockets are used with 2 idler sprockets to manipulate the chain so that we get the correct motion to convey the jute through the system. Shown further is some of the motion of the device. On the left is the side view where you can see the spacing between gripping rollers and how the fraying fins are intertwined so that it is constantly hitting the jute stem. We also have a view of the assembly from the top and the motion there. While it does look great, we do have a few issues. With a large enough bundle, the dowel rods do get jammed. This is in part to the power source being used and would be less likely to happen with the actual 15 horsepower motor and the full-scale machine. Another issue is that we ran into to is that some of the sheet metal we had manufactured was a bit too thin, so we'd like to increase the thickness as we noticed some vibrations when we were testing the machine. Another point of potential improvement would be to replace the slotted flange bearings with fixed pillow block bearings for better stability. And the last point is that the machine is fairly heavy. Before I get to conclusion, I want to briefly mention expected cost. Before taking into account bulk buying and supply lines, the total for the machine turns out to be near $1,100, without including the cost of the power source. This price is within the price range setup of other machines. On the high end, we see $2,000, and on the low end, we see $1,500. But for the most part, many of those machines are costing around $2,000. Overall, the design presents a novel method of fiber stripping, is able to separate fibers from stems, and is easy to manufacture. However, the cons are that it is cumbersome to assemble, uses rubber and low longevity items, and the fraying method is sometimes unreliable, requiring us to put the stem through twice to fully remove the fibers. From this, we reviewed our goals set out at the beginning of the semester. We were able to design and create an automatic decorticator that can be operated by one user. This design minimizes the uses of retting. The design mostly was able to strip fibers, occasionally having to run a piece of jute through again. The design is manufacturable and serviceable in Bangladesh. It is safe and affordable. And the only general downside is that it does not have the throughput to rival current competitors that mulch the stems. Overall, while this is a solution to the problem, this one is not the final solution. More design iterations should be considered, and the primary issues currently are inconsistent decortication and use of materials that have low longevity. Thank you for watching, and I hope that you enjoy our booth.